We're going to talk about inverse functions. Let's start with a simple function, f of x equals 2x plus 5. So f of 3 is 3 times 2 is 6, plus 5 is 11. Okay, so what we want to do is find another function so that when we punch in 11 for the input, the output is 3. So in this f function, if the input is 3, the output is 11. Let's do another one. What is f of 7? Um, so 2 times 7 is 14 plus 5, 19. Let's do one more, f of 5. I guess I should have put them in order, 3, 5, 7, but 2 times 5 is 10 plus 5, 15. Okay, so we want to find a mystery function. For now, it's not the mystery function, a function that takes 11 into 3, 19 into 7, 15 into 3. So it reverses what this function does, or it undoes what this function does. This function takes 3 into 11, 5 into 15, 7 into 19. We want to do the reverse. We want to take the 11 into the 3, and then, sorry to interrupt myself, but because I got all excited about this, somebody could be saying, well, how about 11? If we plug in 11, we get 22 plus 5, 27. So 11 doesn't work. Rather, yeah, if we plug in 11, this output, we get another output, a third output, I suppose, or a second output. The point is, we want to find a function that does the opposite. Now, we could think of well, so let's write down what we want. We want another function that undoes what f does. So we want to do the reverse. Now, we can think this through, not too difficult, without too much difficulty, because we can think, all right, the input gets multiplied by 2, and then that product gets added to 5. So how do we get the 11? Multiply the 3 by 2 and then add 5. So if we undo those steps backwards, we have to divide by 2 and subtract 5. But the thing is, there's an order of operations going on here. We multiply by 2, and then we add 5. And when we want to undo that, we have to do them in the reverse order. It is like putting your socks and then your shoes. You don't take off your socks first, even though those are the first ones you put on, your socks. You don't take off your socks first, you take off your shoes, which was the last thing you did. So if you want to undress your foot, if you put socks and then shoes on, the way you undo it, the way all of us do it, is we take our shoes off, which was the last thing we did first, and then we take our socks off. So the same thing happens here. Pretend those are the socks and those are the shoes, because that's the order in which those operations are performed on X. So we multiply by 2 first, then we add 5. How do we undress to leave the X back to original state? We undo the addition by 5, so we subtract 5, and then we divide by 2. So the inverse function, the formula we want, looks like this. X, take away the 5, and then divide the 2. But this fraction, because it's covering all of the x minus 5, indicates we have to do x minus 5 first, and then divide by 2. So that becomes last. Some of us may be thinking, wait a minute, I thought multiplication and division have to be done first, and then addition and subtraction after. That is true, except that whenever we have a fraction line, there is a hidden parenthesis on the numerator and on the denominator. So there's a parenthesis here. We don't see it, but it is there. This line works as a parenthesis on top and on the bottom. Every time you have a horizontal line, assume there is a big parenthesis on the bottom or on the top of that line. So will that formula work? Yes. Let's make sure though. If we plug in 11, 11 minus 5, 6. 6 divided by 2, 3. Yep. Plug in the 19. 19 minus 5, 14. Divide 14 by 2, 7. Yep. Plug in the 15. 15 minus 5, 10. Divide by 2, 5. Yep. Plug in the 27. 27 minus 5, 22. Divide by 2, 11. So this formula works. Now we're going to give a name to the inverse. And the inverse function will be f with an exponent of -1. So that is the inverse of f. The inverse, yeah, we call it the inverse of f. And it is the inverse function. Now, before we continue with this, let me talk about unfortunate notation. Okay, unfortunate notation. What is 3 to the -1? Well, most of us remember it is 1 over 3. What is x to the -1? Most of us remember that is 1 over x, and that is completely correct. However, and here's the unfortunate part, if we have f to the -1, that guy is not 1 over f. If we have a function, whatever the function is, if it is a function, and the way we can, well, we sort of have to know what's going on. If we have a number or a variable to the -1, that's the reciprocal, that's fine. But if we have a function that is not the reciprocal whatsoever at all, it is the inverse function, the function that undoes the function, the original function, that goes the other way. Yeah. It is unfortunate because we're using the same kind of exponent for two different ideas. And I have mentioned this before in other videos. Every time we're using the same thing for two different ideas, objects, people, that creates confusion. So if two people in my classroom are called Michael and I say, Michael, answer the question, then they may not know who am I referring to. You know, I have had classes with 3 students or 4 students with the same name, the same first name. So that's kind of happening here. We're using the same notation, but different ideas. So we have to be aware that we are talking about a function versus not a function. Even in trigonometry, I see students when they see, and by the way, this is very universal. It is widely known. So this is the name of a function, sine, and its inverse would be this. We also, some people, to avoid that confusion, they label it as arcsine, which is the same thing. So sine inverse, f inverse, reciprocal of x, reciprocal of 3. So we got to be aware of the differences. So this is, some people, to avoid that, call this arcsine. So they don't have to put the -1. And that's perfectly fine, except that we still have the same notation for any other function. So it's better to do this, to in my opinion, to put an exponent of -1, and just remember that if you have a function, then we are not doing 1 over that. Even our calculators, they have an inverse function, right? And that doesn't mean 1 over sine. That means the undoing of the sine. and this is not trigonometry. I'm not talking about trigonometry, but I still want to just show you one example. So many of us know that the sine of pi over 4 is the square root of 2 over 2. So what is the arc? So what can we say about the arc sine? Okay, so you don't need to know trigonometry to know this. Even if you don't know what that number or that number means, we can see them, okay? So if the sine of this input is equal to that output, what is the arc sine or the sine inverse of what equals what? What can we say? Now, let's go back to this. If f of 3 equals 11, oh, I didn't put this down here, but let's write this down over here. The inverse of 11 has to be 3. And we did that earlier in this video. The inverse, or the inverse function of 11 is 3. The inverse function of 19 will be 7. The inverse function of 15 is 5. The inverse function, this particular function of 27 is 11. So the inverse function reverses. We got 3, 11, 11, 3. 7, 19, 19, 7. 5, 15, 15, 5. 11, 27, 27, 11. So if we know, even if we didn't know any trigonometry, but I'm telling you, sine of pi over 4 is square root of 2 over 2. What can we say about the inverse? Well, it has to be square root of 2 over 2. The sine inverse of square root of 2 over 2 is pi over 4. So given this information, we can draw that information. And we don't have to know trigonometry. If we assume this is true, this has to be true. And we are assuming that there is an inverse. Now, this gets a little more complicated than when we are talking especially about sine, because there is some domain and range issues we have to, especially domain issues, we have to address when we are talking about sine. Even though there's more things we would have to address to really understand the inverse of the sine and cosine and tangent, the fact remains that the inverse swaps the x and the y. This is x, this is y. In the inverse, they get reversed. This is y and this is x. Although we rename the variables, because when we wrote this down, we didn't say f of y equals y minus 5 over 2, although that actually makes sense. We rename the function because it doesn't matter what we call it, and typically we call the input x. So what we are doing is resetting this back to as if x was the original variable. That is very interesting. Okay, so the point I wanted to make on this second page of this video is that we have an unfortunate notation. Please get that in your mind. When we put a negative exponent, -1 as an exponent of a number or a variable, we are talking about reciprocal. What is unfortunate is that we have exactly the same notation for a completely different idea. So this is an interesting example, because if you go on and take trigonometry, or if you have taken trigonometry, perhaps at one point you got confused. I still remember way back when I was very young, I remember thinking, isn't that 1 over sine? And it really threw me off when I saw that the first time. And then it took me a little while to figure out, oh, okay, so we are talking about a different idea altogether. It has, that -1 has nothing to do with this. It took me a couple of days to realize what was going on. Yeah. By the way, learning oftentimes doesn't feel very comfortable, because when we are given a new idea, we're off balance. We don't know what's going on. We're confused. We are trying to use old ideas into the new ideas, and and that is a little uncomfortable at first, but it's just learning. What I mean by that, this is just a little bit of mental pain, but that's it. And then after a little while, we sort it out in our minds, we figure out what's going on, and then we move on. Yeah, yeah. So don't be too afraid of that uncomfortable feeling of getting confused and not knowing what's going on, and asking a lot of questions. You know, learning being a learner is a humbling experience, because we have to admit to people, hey, I don't know this. Can you explain it? Can you help me? Can you tell me? I'm confused. It's very humbling, because we have to be very vulnerable when we're asking those questions. And there's nothing wrong with that. Well, except that it causes a little bit of feelings. Now, okay, so this is the general idea of what the inverse does. We got some notation. And now there is a fact: not all functions have an inverse function. Now the key here is in the two words, inverse function. All of them have an inverse relation. All functions have an inverse relation, but the key is not all of them have an inverse function. And so we're going to focus on the inverse function. What I mean by that is, actually, let me give you an example. Example 2. Okay, and this is more of a set example. So let's say we have a function f that is defined by set of pairs. So 1 goes with 2, and 2 goes with, oh, that's going to be confusing. Let me change that. Sorry about, where's my erase? There it is. I really want to use completely different numbers. So 1 goes with 7, 2 goes with 7, yep, and 3 goes with 8. That's a simple function. It has 3 inputs, 1, 2, 3, and 2 outputs, 7 and 8 only. So what this is telling us is that f of 1 is 7, f of 2 is also 7, that's not a problem, and f of 3 equals 8. And there's no formula. There's no, x plus 7 minus, or x minus 2. There's no formula. I'm just telling you, spelling out input, output, input, output, input, output. Okay? Does that have an inverse function? Now, let's recall what the inverse does. The inverse switches x's and y's into the other way. So at first sight, all we have to do is just swap those two around. So the inverse, I'm going to say, I'm going to keep that blank for now. The inverse will be 7, 1. So reverse the x and the y. 7, 2, 7, 2, and then 8, 3. Okay, that is cool. But, so this is an inverse because it flips x's and y's, but this is no longer a function. That's the problem. We don't have a function anymore. Why not? 7 goes with 1 and 7 goes with 2. We cannot have a function where the output is ambiguous. Is it 1 or 2? Okay, so the question is, what is the output of 7? Question mark. Is it 1 or 2? Question mark. And we cannot say, well, it's both. No, no, in a function, the outputs are unique. Yep, so this is a definition that we have. It's not a fact. It is a fact only because we made it a fact in the sense that we are making it a definition. In a function, an input may not have more than one output. In fact, every input must have exactly. Now, by exactly, we mean no less than one and no more than one, exactly one output. Yeah. Yeah. So we cannot have two. We cannot, choose one day and choose the, no. It doesn't, it has to be one output. So we came up with an inverse relation, but not an inverse function. So f as in this page, and by that I mean this example with that f is not a function. Okay, so we don't want to have functions. Now this is a function nonetheless. Yeah, so let me note that. Note f is a function. But the inverse is not a function, it is simply a relation. So a relation is just any set of points, let me remind you. So this function is not invertible. So if the inverse of a function is not a function, then we say that the function is not invertible. Or let's put it the other way. If f inverse is a function, and let me add more to this, assuming f was a function too, then we say f is invertible. So invertible means that when we find the inverse, what we obtain is also a function, which means that every input has a unique output, exactly one output. Yeah. Every input has exactly one output. I was pausing because I was thinking there's several ways to say that. Every input has exactly one output is the same as saying every input has a unique output. So be aware of the different ways of saying that. So invertible means that that when we find the inverse, we will find a relation, but that relation may or may not be a function. The key is that we want to concentrate on functions whose inverse are functions again. Otherwise, we don't really care about, well, it's not that we don't care, we have to treat them differently. Yeah. Now, they are so important, those functions, we have a special name for them. We call them one-to-one functions. So a one-to-one function is the one that for any two different inputs, comma, the outputs are also different. So that's one way to put it. There's a couple different ways to put it, but that's one way to put it. So what messed up this function? The fact that 2 7s came out. there's a repetition. The 8 didn't matter. That's not a problem. Had there been 2 8s, then that would have contributed to the problem. But here, the 2 7s is what messed this up. This function is not one-to-one because two different inputs have the same output, violating the property of one-to-one function. So one-to-one, they cannot have a different, outputs cannot have different inputs, and inputs cannot have different outputs. Yeah. So that leads to what is called the vertical line test. No. The horizontal line test. Okay, so line tests. Okay, now we have two line tests. We had one earlier, and now we have two. So the vertical line test tests, the vertical line test, there's no comma in there. That was just a long noun. The vertical line test tests whether a relation is a function or not. So remember, the vertical line test, we'll do some examples. And then we have the horizontal line test, which we did not have before. Tests, but that's kind of confusing. This is the verb and this is the noun. So the horizontal line test, that's a noun. Tests, here I didn't put an S, tests whether a function is one-to-one or not. By the way, see, one-to-one turns out to be exactly the same thing as invertible. So that's another place where we could get confused. One-to-one is the same thing as invertible. It turns out to be the same. All right. So as an example 3. Okay, let's look at a circle. Is it a function? Function, question mark? Of course, no. Why not? Because we can draw a vertical line which will cross the graph at 2 points. So the answer is no. And I want to keep the video efficient, so I'm not going to write all of that. But that's the advantage of having a video. I can speak fairly quickly. So again, this is not a function because it does not pass the vertical line test, which states that if there is a vertical line that crosses the graph at 2 points, then we don't have a function. Okay, so how do we fix it? Well, we have to split that into two functions, the top and the bottom. So now we got two functions. Okay, so the circle as a whole is not, but there is now a top function and a bottom function. So if you wanted to draw that on a graphing calculator using y, you have to have y1 and y2, two functions, one for the top, one for the bottom. It doesn't matter which one you do first, and then that will work. The two get together. Now, on a graphing calculator, you may not be able to see the sides too well because the pixels are not close enough to see that the two graphs are closing together. But that's a different matter. It has more to do with the pixels and the drawing, but indeed we do have two functions and together they make up the circle. Okay, so the next question is, are they one-to-one? Are they, oh, What do you know? I'm running out of ink again. So we're going to use a different writing instrument. So the question is, are they one-to-one? Question mark. And the answer is, again, no. Individually, they're not one-to-one. Why not? Because we can draw a horizontal line which crosses the graph at 2 points. If we can do that once, that's it. The whole thing is messed up. It's not one-to-one. Same thing here. Now, we have to have the test twice, one for each one of the functions. So they are functions, but they're not one-to-one. No. Can we fix that? Sure. That's interesting. So now we have to have an upper quarter, upper left quarter, a right quarter, upper right quarter, a lower left quarter, and a lower right quarter. Pretend those are just quarters of a circle. Now we got 4 1-to-1 functions. Okay, so can we fix it? Yeah, but then we have to split it. And that is done actually frequently, or okay, it's done periodically, not too frequent, but yeah, it is done. So we have to know whether a function is one-to-one or not. It is super duper 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 super important to know whether a function is one-to-one or not, because then we can undo the function. We can undo things. In fact, well, again, this is something that we're going to see in the future, an exponential function. So we haven't seen exponential functions, but exponential functions have an asymptote, a horizontal asymptote, and they go like this. So are they one-to-one functions? And the answer is yes. So even though we have not seen exponential functions mined, we haven't seen it, but they look like this. They get closer and closer to this horizontal line, and then they increase. This is one kind, and there's the other ones that go down, but this is one kind. They go up like that very quickly. Okay, so that graph is one-to-one. This is one-to-one. And we may be thinking, okay, that's cool. So what? You know, that means that we can solve exponential functions in a unique way. We can do the reverse, which are logarithmical functions. So there is, having inverses are very important because that allows us to solve equations by undoing whatever the equation is doing to the input. Yeah, yeah, or whatever the equation is doing to the expression we're solving for. Yeah. So having inverses are very important. Logarithms have inverses. And by the way, the inverse is also invertible. The inverse of a function, assuming that the inverse exists, is invertible. So there is no inverse for this. And by that, we mean inverse function for that. If we wanted to find an inverse function, we have to split the problem into each one of those into 2. Since those were a split of that, we split the original circle into 4. And then we have invertible functions, not an invertible function, not even an invertible relation. And by that, what we mean is, so invertible means that we have to have a function. All right, let's look at the graphs again, more about the graphs. So graphs of inverses. And by that, inverse but when we say inverse, we mean inverse functions. Okay. So 4. Okay, let's say we have a quarter of a circle, just one quarter, Pretend that's a quarter of a circle. It starts out with -5, 0, assuming that the circle has radius 5, and ends, it goes around this way and ends with 0, 5, assuming that the circle has center at the origin. So there it is. So that didn't look too roundish, kind of looks more parabolic, but pretend that is a circle. So the question is, what is the picture of the inverse? Okay. Now, let's recall what the inverse does. See, this idea in the first example is crucial. Please remember that. The inverse reverses the input and the output. So 311, which was a point on the graph of this function, is not a point on the graph of the inverse, but we can figure out a point. Instead of 311, we would have to have 11, 3. Well, that's what's going on here. Instead of 0, 5, we're going to have 5, 0. So 0, 5 leads to 5, 0. We have to actually switch the x and the y. -5, 0 goes to 0, -5. Okay, so the initial point, the starting point goes from here to there. So now we go from here to here. But the question now remains, do we arch this way or do we arch the other way? Because there's two ways to, or do we go straight? Well, we don't go straight because, so the question is, what, barnacles, what do we do? Well, 5, it's interesting, I picked 5 because there's a triangle I know, and you probably know it from geometry, that looks like this: 3, 4, 5. It's a right triangle, and we know from Pythagoras that 3 squared plus 4 squared equals 5 squared. Now, because that is 9 plus 16, and 9 plus 16 is exactly 25. So we have a triangle that is 3, 4, 5. Okay, and I'm going to use that here. So there's a point -3, 4. So there's a point that is here at -3, 4. Because the radius is 5. So if you go -3 to the left and up 4, we're going to end up with the same kind of triangle, 3, 4, 5, except that the 3 goes to the left. So now we have a -3. But it is the same thing. So that point belongs to this circle. Well, what point belongs to the inverse? And by the way, I meant a quarter of a circle. What point belongs to this other quarter of a circle? Well, it's got to be 4, -3. So we got to go 4. And if we were going in a straight line, we would have to go 4, -1. Okay, because the straight line, think of a step. If we were going in a straight line 45-degree angle, because that's 45 degrees, if we are at 0, -5, and we were going at a 45-degree line, then the next point would be 1, -4. And then we will go to 2, -3. Boy, that it's not going to reach. Well, we'll see. 1. Oh, I'm going the other way. 3, -2. 4. I'm going to start putting the coordinates here. -1. And then eventually we reach 5, 0. So I'm not stating that we are going on a straight line. If we were going on a straight line, those are the coordinates we will have: 0, -5, 1, -4, 2, -3, 3, -2, 4, negative 1, 5, 0. Okay, so negative 3, 4 now goes to 4, negative 3. If we were on the line, we would have 4, negative 1. So this point has to be farther down, which now we know it means that we have to curve this way. See, this point here would be 4, negative 3. It has to go lower than 4, negative 1, thinking we were going in a straight line. I know this is a long analysis, but we don't have to do it every time. However, it is good to practice. So let's draw the two on one graph. So this is what's going on. If you have a quarter of a circle going this way, the inverse is going to be here. So we see some symmetry, but it's not symmetry across the y-axis. Otherwise, we would have that. It is not symmetry across the x-axis, because then we would have this. What we have is symmetry diagonally. Okay, let's look at another example. Example 5. Let's look at this graph now. And it is a good idea to take the time and really understand this. We have to step away from thinking that math is simply about punching numbers on a formula, and that's it. That's not, if we think of math as just punching numbers into a formula, you just need to know what formula to use, punch numbers. That is a little part of it. It's kind of like saying composition writing is just about knowing how to spell words. Yeah, yeah, you can spell beautifully, but you may not be able to put together a paragraph. You know, we have to have some coherence and some main idea, and we have to develop the idea, and we have to take into account the audience. And there is so much about writing. And whenever I write, I have to write and edit and edit and edit, and then I show it to somebody, and they help me and give me their input, and then I tell them, no, and then I fix it according to their input. I give it to somebody else, they give me their input, and then sometimes I disagree with their input and I fix some of it, but not some of it. You know, writing is a whole process. It's not just knowing how to spell words. That's just, I mean, yeah, we have to spell well. But in mathematics, the reason why I'm going there is kind of the same. If we just learn how to punch numbers onto a calculator or into a formula, that's just as good as knowing how to spell. Yeah, you might be really good at that, but can you really think through? That's the challenge. So the reason why I'm bringing that up is because we want to, I could have told you how the graph of the inverse is in 2 seconds. Well, maybe 4 seconds, you know. But we want to understand what's going on. We want to own the idea, the concept. Anyway, sorry to go into a little tangent, but I think it's fruitful to know why I'm taking my sweet time with explaining how to draw the inverse. 5, 0. So pretend we start with this 0, 5. Now this is very interesting. So we're going to swap those two, and we're going to end up with 0, 5. We're going to swap those two, and we're going to end up with 5, 0. Well, those are the same points. There's a point here. Well, let's look at 4, 3. So 4, 3 is here because of the 3, 4, 5 triangle. That's why it was a good idea to have 5 after all. And then we flip that around. And oh, by the way, up here, sorry to interrupt myself, we have 3, 5, 3, 4. Yeah, this should be bowing a little more now that I look at it. But anyway, so the um, scale is off a little bit, or my graph is not particularly round. It's not, it should be more round than this. This is a little flat. But anyway, what I want to show though is that when we flip those two around, we end up with this point. And when we flip those around, we end up with this point, just the same way as when you flip those two around, we end up with this. When we flip those two around, we end up with that. What that tells us is that, and that is going to happen for every point on this curve. So the inverse turns out to be itself. It is the same thing. We're still going to end up with 3, 4. Why? Because we have 4, 3 in the picture, in the original function. So this is f, and this is f inverse, and they turn out to be the same. 4, 3. All right. So here they were the same. Here, this is the function, and this is the inverse. By the way, the inverse of the inverse is the function. So the inverse of this is that. The inverse of that is that. So they're inverses of each other. But this is the function, and this is the inverse. So how come here they're opposite? Here they're the same. Well, it has to do with the line. So now I'm going to tell you what's going on. Every time you got a function, it doesn't matter what function you have. Yeah. So example 6. So now I'm going to tell you. So when you have a function that is one-to-one, so that's like an S, we're going to reflect that over this line, y equals x. This is not part of the inverse. That's why I dotted it. It's an auxiliary line, and it's going to show us what's going on. And we have to draw a picture that is symmetric along this line. So if you turn the page this way, then whatever I draw has to be symmetric across this line. So we have to have this. I'm going to attempt to do this. So let's see. It curves this way and then this way. Yeah, that's not perfect, but it kind of does the job. So the inverse of this is that, and the inverse of this is that, and they have to be symmetric across this. Y equals x. So if this is a function, this is the inverse. So here, that's what happened. Because this drawing is already symmetric with respect to this, the inverse is itself. Now, it's not like the two together make a new function. No, no. Those are two functions, 1 and 2, 1 and 2. Well, they happen to be the same, so 1 and 2, 1 and 2, 1 and 2, 1 and 2. And again, now we can see why. Yeah. And the reason is because we have to flip x and y. This line is precisely where they don't flip. It's the neutral zone, so to speak. It is where things don't change under inverse. When I'm doubtful of how to draw a picture, I literally just draw a few points on the function on the graph. I actually label them. I flip them, the numbers, and then I draw carefully the other points on the inverse. And that's how I figure things out, to be honest. Yeah. Okay, so that's example 6. Okay. How do we go about finding the inverse formula, the inverse equation? Okay, so algebraically, example 7. Okay, we want to find so the goal is to find the inverse. And let's start with this example 1, but I'm going to label it example 7. So I'm going to use the same example. So find inverse, and by find we mean find the formula, find inverse of f of x equals 2x plus 5. 2x plus 5. So it is the same example we started on this video with. Okay, so there is a series of steps we follow, an algorithm. Okay, the first thing I want to do is change this into a y, a variable, a single variable, because we're going to be manipulating that variable. So step one is to rename the function as y. Y equals 2x plus 5. So I'm going to say use y instead of f of x. If we already have y, then don't worry about step one, then it's done. Step two, okay, is about swapping all the x's with all the y's. Swap all x's with all y's. So instead of having y equals 2x plus 5, we're going to have x equals 2y plus 5. Just everywhere where you see an x, write a y. Everywhere where you see a y, write an x. If there are two x's, put two y's. If there is two y's, put two x's. Okay. There we have it. That is already the inverse, because the inverse swaps the x and the y. However, we want a formula, an explicit formula for how to obtain the outputs of the inverse. So what we're going to do is solve for x. I'm sorry, solve for y. So step 3, solve for y. Okay, so for instance, we can subtract 5 from both sides of the equation. So x minus 5 equals y, 2y rather, 2y. And then we can divide by 2 to leave the y alone. So x minus 5 over 2 equals y. And then the last step is to rename the function, the new function. This is a new function. It is not the same function. It is a different function because we swap the x's and the y's. So we rename them with the correct name. So rename. So now we have the inverse of the original function is, and then just write down the function, x minus 5, all of that over 2. So the inverse of this function, whoops, the inverse of this original function after doing those steps is this. And we put f inverse. Example 8. Some examples are way more complicated than others. As this one. This one is pretty complicated. Find inverse of f of x equals 3x plus 4 over 5x minus 6. Whoa, that's going to be an issue. By the way, step 1 is easy. Step 2 is, oh, I'm sorry, step 1, super easy. Step 2, easy. Step 4, really easy. The only one that is difficult is 3. This is the biggie. The other ones are really, really, really easy. That's where you're going to show, whether you can do this or not. Step 3 is the big one. Okay, so step 1, anybody, well, most people can do it. Step 1 is y equals 3x plus 4 over 5x minus 6, no problem. Step 2, x equals 3y plus 4 over 5y minus 6, no problem. I mean, that was a little more complicated because I got to keep track. Okay, which one was an x, which one is the y? Okay, I cannot be distracted. I have to focus a little bit. Now here's where we need the algebra. Step 3, we got to solve for y. But there are two y's involved, and they don't cancel off, of course. First, we're going to multiply on both sides by the denominator. So x times quantity 5y minus 6 is equal to 3y plus 4. Let's distribute. 5xy minus 6x equals 3y plus 4. Let's move the y together. We're solving for y. The two y's are spread out over the equation, but we want the y's to go together. So we're going to subtract 3y from both sides of the equation. While we do that, we're going to add 6x to both sides of the equation. Subtract 3y from both sides of the equation, add 6x on both sides of the equation. So now we have 5xy minus 3y equals 6x plus 4. Okay, remember we're solving for y. Now that the y's are together, factor them out. So y quantity 5x minus 3 equals 6x plus 4, which means y has to be 6x plus 4 divided by 5x minus 3. Finally, we have the y by itself, and now we can finish with step 4, which is an easy one. Rename the function as inverse of x is 6x plus 4 over 5x minus 3. Okay, let's do another problem. But this problem that we're going to do is more complicated because it has to do with domain. Example 9. Okay. Yeah, this is an interesting, please pay attention to this example. This is not a simple example, I think. If we let me tell you where the example is going to come from. If we have x squared plus y squared equals 25, you should know, and if not, let me remind you, that this is a circle of radius 5, center at the origin. So far, so good. But we did say that is not a function. Okay, let's say I want to take the inverse of this algebraically, which is going to give us that. Fine, we can do the picture, but how about the formula? What formula works for this guy? So I'm kind of referring back to our example 4 of today's video. How do we go about that? Okay, first let's where's the circle? There's a circle. Okay, let's start with a circle, which is what we have. That's not a function. That is not workable, first of all. So I haven't written the actual problem yet. I'm showing you where I'm getting the problem from. Okay, so let's solve for y. Y squared equals 25 minus x squared. We subtract x squared from both sides of the equation. Y equals plus or minus square root 25 minus x squared. Okay, so that's the two y's corresponding to that and that. Okay, but I don't want to have two, so we're gonna focus, we're gonna narrow our view instead of two. So these are two functions. Let's focus on one function. So y equals just the positive part, which is this half. Now, can we find the inverse of that? No, because it is not 1-to-1. It doesn't pass the horizontal line test. So how do we change it? So, okay, so we went from 2 to just 1. So these are the circle, the half a circle, but even the half a circle is not good enough to be invertible. So what we do is restrict the domain. So the domain of this is all the numbers from -5 to 5. So what we're going to do is 25 minus x squared, comma, we're going to put the domain from -5 to 0. Because this goes from -5 to 5, so the implicit domain is from -5 to 5, but we want now the domain to go from -5 to 0. And that will give us only quarter of the circle as opposed to, so we change the function from, or this was not even a function. This is not a function, it is two functions. Change it to that. So there was a change from here to here. That's not the same y. Now we pick one. That is still not invertible. So we change it to this, restricting the domain. Now we're good. By the way, and this is not as easy to do, what is the range of this function? It's not a bad idea to plug numbers in. So, okay, so I was just explaining with this where the problem will come from. So here's the problem for example 9 problem. Okay, find inverse of f of x equals the square root of 25 minus x squared, comma, from -5 to 0. That is important. If we don't put that, then we have an implicit domain, which is the entire half of the circle, which is not invertible. So not every function is invertible. Okay. Now, let's go through the steps first. And then we have to do more when we get to an answer. So this is a tricky question. Some of you may be thinking, man, this is not something I can just solve and get an answer and move on. No. And that is the beauty of this math stuff we're learning. A lot of the problems we encounter in everyday work and life for that matter are not that simple. Just do this and then we move on. No. We gotta really analyze it, reanalyze it, and concentrate and focus and to get to a solution. And this math work allows us to do that very efficiently. We can analyze a problem very, very efficient, that is complex, very efficiently. Anyway, so let's go through the steps. Step 1, remember y equals square root of 25 minus x squared. Step 2 was to do x equals square root of 25 minus y squared. Okay, so we're swapping x's and y. Step 3 is the big one, solving for y. So square both sides, x squared equals 25 minus y squared. Let's add y squared to both sides of the equation while we subtract x squared on both sides of the equation. So y squared equals 25 minus x squared. Okay, so here's the beginning of the problem. Y is, or the complications. Yes, the square root of 25 minus x squared, but we have two possibilities. So the question is, which one are we going to pick? Which one? Plus or minus? Because the plus is going to be the top of the circle, the minus is going to be the bottom of the circle. Furthermore, we have to ask ourselves, because invertible functions, rather the inverse of our invertible function is an invertible function. That sounds like a tongue twister, but that's how it goes. The inverse of an invertible function is also invertible. What I mean by that is, even if we choose plus or minus correctly, and there's a correct and incorrect way to do this, in this particular case, we still have to ask ourselves, wait a minute, which one are we going to do? The left half or the right half? So let me make a note of that. In addition, to having to pick or choose plus or minus, comma, we also have to choose domain from -5 to 0 or from 0 to 5. And it's not obvious. Don't assume that because this is -5, 0, oh, the domain is -5, 0. No, in fact, it is not the case. Okay, so in step 3, we're stuck in step 3 at this point. Y equals plus minus 25 minus x squared. In addition to that, we have to decide whether we have to do from -5 to 0 or from 0 to +5. Okay, so let's back up a little bit and look at the function. So the original function had input. So this is the original f, had input from -5 to 0. Now let's analyze the output by simply plugging in here. In fact, I'm going to do it here. F of -5 is the square root of 25 minus -5 squared, which is square root of 25 minus 25, which is the square root of 0, which is 0. And that makes sense because that's a quarter of a circle. Which quarter of a circle? This one. So the output of -5 is 0. What is the output of 0? Well, let's do it. F of 0 is the square root of, now I'm still working with the original function. 25 minus 0 squared, that is the square root of 25, which is 5, which makes sense because the output of 0 is 5. Okay, so this is the original function. In the inverse function, the tables have to be reversed. Now, keep the same x, keep x and y, but the numbers have to be exchanged. So instead of putting down -5, 0, now we're going to put 0, -5, 0, -5. Instead of 0, 5, we're going to put 5, 0. That is how we obtain the domain of the function. And also that tells us whether we're going to pick plus or minus. See, the domain of the function is 0, 5, 0, 5. So y has to be, I haven't decided whether to do plus or minus yet. But what we do know based on this is, remember, this has to do with the domain of the F inverse based on the domain of the F. Figure out some extreme values, swap, voila. Now, yeah, that's pretty much it. So the domain goes from 0 to 5, which was not obvious because our original function was going from -5 to 0. That wasn't obvious. From 0 to 5. The range goes from -5 to 0. Now this -5 says that we have to pick the negative. Otherwise, there's no way we're going to get the negative. See? Negative or positive. This is the principal root, which gives us positive numbers. So there's no way we would obtain a negative number with the principal root unless we ourselves pick the negative. Okay, so that negative came from this information. 0, 5 came from that information. So now we have made the decision that the inverse is negative of square root of 25 minus x squared, comma, from 0 to 5, which is 100% consistent with example 4. Example 4 is this. That was this is our original function. The inverse goes from 0 to 5 in the input, but we do the bottom, which means we are doing this. Do go over problems. Problems are convoluted. They're not easy because we have to analyze the function. If it takes you 10, 15, 20 minutes, even half an hour to do one problem, that is time well spent. We gotta get away from the mindset that you just, plug some numbers or follow some steps and that's it. If we become a person who just follows steps blindly, it is too easy to pull the rug from under ourselves. Because all I have to do is just tweak the problem a little bit, and then the steps are not going to work as nicely. And then if we don't know what we're doing, we're going to be stuck with the process. So we really have to understand the concept. The deeper the conceptual understanding, the harder it is going to be for anybody to pull the rug from under ourselves. There's one more thing I have to address. 9. So how can we tell whether a given function is invertible or not? How can we prove that a given function is one-to-one or not? Okay, there is a couple ways to go about this. If the graph is reasonably well known, okay, so if graph is reasonably well known, then draw it and show horizontal line test. Okay. And we're going to go over that again. There is, I'm going to say a little more in detail, and I'm going to explain what I mean by this in detail. I'll tell you what I mean by that. If you suspect it is not, if you arrive to the conclusion that it is not, the function is not one-to-one, then provide two different inputs that have the same output. Provide specific inputs, two of them, exactly two of them, so their output is the same. Okay, this is to prove that a function is not one-to-one. And when I say In detail, I mean to prove that something is not one-to-one. And then there is a third thing. If you suspect the function is one-to-one, find the inverse. Find the inverse correctly. Okay, so use that if one-to-one is, if you know that the function is one-to-one, one-to-one. Use that, that's a shorthand for one-to-one. It's not 1 minus 1, it's just a dash, 1, 2, 1. I'm just gonna write it, 1, 2, 1. Anyway, if you wanna show that something is not one-to-one, then use this bullet, not one-to-one. This could work for both, but when you wanna be specific, you wanna show not one-to-one. Okay. So example 10 is y equals x squared 1-to-1. And the answer is no. Now, this is a super well-known graph. If you don't know it, then get to know it. Draw it a couple times by hand on a nice, grid, and then just figure out the inputs and outputs. Go through that. Anyway, so this is a nice parabola. And it's not one-to-one because it fails the horizontal line test. And all you have to do is this. And this is a super well-known, so by horizontal line test, comma, y equals x squared is not one-to-one. See, the question is not asking find, the answer. It's asking a question, a more general question. Is this one-to-one or not? And why not? Well, no, and we have to explain why not. Because it fails, there's a horizontal line that crosses the graph, which is well known at 2 points. Alternatively, we can answer this same question algebraically. So algebraically, comma, prove that y equals x squared is not one-to-one. Okay, so this is a command. This is not a question. So we want to prove something. That's, in this case, super easy, and we don't have to draw a picture. So the other way to go about it, by the way, I meant to put a name for the function. Where's my eraser? Did anybody? Oh, that thrown far away. I don't know why. Yeah, like you were gonna tell me. Oh, it's over there, Mr. Selder. Anyway, so let's label this as f of x. There we go. And you're gonna see why. And then I'm gonna go back to y and tell you how to deal if you had only a y in there. Anyway, so f of x equals that. Is it one-to-one? No, it's not. We answered that question back here. Now that we know it is not, algebraically, without a picture, how can we tell? Well, take two numbers, say f of 7. Of course, that is 7 squared, which is 49. And f of -7, which is -7 mind squared, quantity squared, equals -7 times -7, 2 negatives, so that's still 49. That's it. Since two different inputs, 7 and -7, comma, have the same output, comma, 49, comma, f is not one-to-one, because we cannot have that two different inputs have the same output. And all we have to do is expose that situation once. So be very, very, very specific, super duper specific. So actually write down the numbers that you suspect will cause this not to be one-to-one. And there are many of them, 3 and -3 and 5. Please do not put x and -x, because then it could work, but we don't. When we are negating, when we are proving that something is not true, all we have to do is provide one specific example, and that's it. Please get into that mindset. When we are proving that something is not true, in general, just provide one example and be done. Okay. Now, to prove something is one-to-one, it is, again, you can use, so, okay. Let me give you an example. Sorry to interrupt myself. So prove y equals x cubed is one-to-one. Well, y cubed, rather x cubed, is well known. It is an s function. It's not really an s, but sort of. It's an s if you look at it the right way. I think if you flip it, no, you're gonna have to. Anyway, it's sort of an s. It's not really an s, but sort of, because an s goes like this. So anyway, it's well known, and you can just draw a few vertical lines, rather horizontal lines, and we can see that they're going to cross the graph at no more than 1 point. So graphically, since the graph passes horizontal line test, y equals x cubed is one-to-one. Yep. Or you can actually find the inverse. Now, before I finish today's video, or this video, because I'm probably going to do more than one video today, I wanted to address this. Remember, in this example, I changed the y equals x squared. And the reason why I changed it to an f is because I wanted to plug in, and I wanted to show what we were plugging in, 7 and -7. So let's say we left it as y. So this is the end of this example. Back to, and it doesn't have to be an example, y equals x squared. Okay. So no f of x. So how can I still show that when we plug in 7, we get, how can we tell what the input and the output are? Well, the notation, so this is in a matter of notation. The notation we use is y of 7. So even though this was not an f of x, we can still use the same kind of notation. So this is not read as y times 7, although in some occasions it could look like y times 7. But no, we read this as y of 7. So y of 7 in this case would be 7 squared, and that is 49. So please keep in mind, sometimes we will use this notation. So in fact, those graphing calculators use that. If you already have a function and you put y of that function in the calculator is going to say, oh, you mean the input is that. The calculator already knows that. So that is widely established. It's not that I'm making that up. Y of -7 is -7 squared, which is 49. So please do not get confused. When we write this down and we have a function, we do not mean y times 7. That has nothing to do with this. This just means plug in 7 for the input. So I guess another way to say this is that y is the same thing as y of x. Yeah. Practice this stuff. Some parts are simpler, some parts are more confusing, especially with the domain of the function. Yeah. Yeah, I guess there's one more thing I need to address, only because of the domain and the inverse. So 12, example 13. But I'm going to start with a function y equals 1 over x, which is well known. And if we don't know it, let's get to know it real quick. This has a horizontal asymptote, rather a vertical asymptote, x equals 0, and a horizontal asymptote, y equals 0. I know this is confusing. Y equals 0 is the horizontal one, and x equals 0 is the vertical one. The graph has two branches. It curves this way. The name of the graph is actually a hyperbola. And it has two branches make one graph. So those two which don't connect form one graph. Each one of those is called a branch. So the domain, we cannot be 0. We cannot make this equal to 0. So the domain, it goes from -infinity to 0. We got to split at 0 and then pick up at 0 to infinity. The range also goes from -infinity to 0 and then from 0 to infinity. And the reason why that is relevant is because when we do the inverse of this function, those two have to be swapped. Okay, but here is the part, example 13, that we need to address. And I don't know if I'm going to do the whole example or not. Pretend we got a function f of x equals 1 over x plus 2. So as you know really well, since you already know this function is a transformation. It's just a shift up by 2 units. So the graph of this function will be 2 units above. So this is not y equals 0 as here. It is y equals 2. And then we still have the same vertical asymptote, x equals 0. And the branches are going to be very much the same. Okay. So you're thinking that's fine. But then what is the domain? The domain still is from -infinity to 0, union from 0 to infinity. The range is going to go from -infinity to 2. Oops, I put -8. That's funny. Negative infinity to 2, skip the 2, and then from 2 to infinity. And what is the relevance of that? Well, let's move on with this example 13. Still example 13. Find the inverse with domain. Okay, so let's go through the steps. Y equals 1 over x plus 2. Swap the x's and the y's. So x equals 1 over y plus 2. I'm going to subtract the 2 from both sides of the equation. X minus 2 equals 1 over y. And I'm going to do something I'm going to flip the two at the same time. So 1 over x minus 2 equals y over 1, which is the same thing as, whoops, over 1, which is the same thing as just y. So rename the function, and the function goes inverse of x is equal to 1 over x minus 2. The domain of this function, with domain, let's add one more thing, and range. The domain of this function, which is going to be fairly clear, we cannot have 2 union 2 to infinity. It's pretty clear. So if we don't put anything, that's understood to be the domain, but then the range, and here's where this information is relevant. When we have the inverse, those two have to swap. So the domain is from negative infinity to 2, and then from 2 to infinity. The range goes from negative infinity to 0, and from 0 to infinity, which before was not necessarily clear. So the range goes from negative infinity to 0, union from 0 to infinity. It is not a bad idea to draw the inverse of this graph. Remember, it has to be a 45-degree angle through the origin reflection, which I don't think is necessarily very easy to draw. Yeah, this one is going to be not too easy. Try graphing the inverse. Yeah, well, again, this topic is not trivial in my opinion. I think we really have to study this topic. It has a lot of nuances, a lot of little things we have to pay attention to. So that's why I don't think it is particularly easy. All right, with this, we will stop this video.